Hello everyone, and welcome back to AISC's Night School, Steel Construction, from the mill to topping out. Today is November 5th, 2018, and this is Session 4, Connection Design as a Fabricator's Representative, presented this evening by Chad Fox of Ruby & Associates. My name is Brent Liu. I am with AISC's Continuing Education Group, and I will be moderating this evening's presentation. I want to introduce tonight's speaker, Chad Fox, PE and SE. Chad Fox is a project manager with Ruby & Associates Incorporated Structural Engineers. He works out of the firm's Grand Rapids, Michigan office. Chad has over 15 years of specialized experience in steel design and fabrication, erection engineering, lifting and rigging equipment utilization, and heavy lift engineering. Some of Mr. Fox's notable connection design projects include the Bank of America Tower, World Trade Center Tower 1, Revel Casino, and the Louisville Cardinal Stadium expansion. Chad is a licensed professional engineer in Michigan and a licensed structural engineer in the state of Illinois. He earned his bachelor's degree from Michigan Technological University and his master's from Purdue University. Chad, thanks for being here, and I'll hand things over to you.
Thanks, Brent. As Brent mentioned, I'm a project manager and structural engineer with Ruby & Associates, located out of Michigan. So Ruby & Associates, we're a structural engineering firm with about 35 engineers, but we're somewhat unique in the fact that the majority of our clients are contractors, steel fabricators, and steel erectors. Rarely do we work for architects. So shortly adding on to my work history, I worked at Ruby & Associates for about 9 years total, but also have about 6 years of experience managing the engineering department for a heavy lift contractor, where we had our own small fabrication shop. So part of my role for that position was oversight for all the internal fabrications and also handled all of the steel material ordering. So I do have some experience on each side of the steel fabrication and design process. So this is the fourth presentation of Night School 18. In session number 1, we've already heard an overview of the entire steel construction process from Drew Twerick, who is another project manager at Ruby & Associates. So some of the material we will cover today has already been touched on by Drew, and will hopefully look familiar to some of you. Also, this presentation ties in closely with the third presentation, a virtual detailed tour of the steel fabrication process, which was presented by Chris Crosby with Chiambro. And fittingly, Chris and I have worked on multiple projects in the past where he retained our services to perform connection design. Here's a list of the 6 main topics that we will be covering today. So first, the Code of Standard Practice as it applies to connection design, continuing with the theme, the overall theme of covering the code in depth throughout this series of Night School 18. Next, we'll walk through the steps taken by a connection designer when both bidding the project and then also to performing the project. I'll highlight some of the common challenges we run into during connection design. We'll also cover items and references that should help both with shop and field efficiencies. And then finally, we'll take a look at some resources, mainly AISC manual and design guides, basically to know that don't have to rediscover the wheel. There's a lot of guidance out there for connection design if you know where to look. First, the Code of Standard Practice, which is located conveniently in the back of the AISC Steel Manual in Section 16.3. So I selected this statement. I thought it was really good within the code to describe its importance. And so basically, unless the contract documents supersede, the Code of Standard Practice describes the official relationships and responsibilities between the parties to a contract. I also wanted to make sure to note that the Code of Standard Practice is also referenced in Section A4 of the specifications, stating that the design drawings and specifications shall meet the code's requirements. So quickly, we're going to knock out a couple of definitions that are used within the Code of Standard Practice. First, the code refers to the owner's designated representative for design, who is responsible for the structural adequacy of design. It is common practice to refer to the ODRD as the engineer of record, or EOR, so we will continue to use this convention throughout the presentation. Also, the code refers to the owner's designated representative for construction, which is typically the general contractor or construction manager, depending on the project delivery type. For section 3.1.1 of the Code of Standard Practice, there are 3 options the engineer of record may select for completion of connection design. First, the EOR can completely design all or certain selected connections themselves. Secondly, the connections can be designated to be selected by an experienced steel detailer. And basically, the detailer would use the AISC manual to select pre-approved connections using the available tables. And then there's option number 3, which we're going to be highlighting today, delegated connection design. And we'll talk about option 3A and 3B, which are newly clarified in the 2016 Code of Standard Practice. So here's an example, is a visual representation of the relationship between parties as envisioned by the Code of Standard Practice, just as an example using the design bid build contractual agreement. And you can see the arrow which points to the position of the connection designer when services are retained by the fabricator or the fabricator erector team. Just a brief history on delegated connection design. Prior to 1960, connections were normally developed by the engineer of record with suggestions from the fabricator. During the 1960s, fabricators like American Bridge and Bethlehem Steel wanted to choose connection types and introduce new fabrication and connection methods, switching from rivets to bolts and welding. Fabricators actively marketed to engineer records that they would take care of connection design and even volunteered to provide the service prior to award for the engineer so that they could review and accept the fabricator's connection design. So if we fast forward to today, east of the Rockies, fabricators are generally still delegated the responsibility. And then west of the Rockies, since the early 1900s, the engineer of record generally designs all of the connections. And a lot of that has to do with the specific connection performance related to seismic design. All right, so now we're going to talk about when the engineer of record selects option number 3 from the Code of Standard Practice, delegated design, what must they provide? So first, per section 3.1.2, they need to provide permanent bracing, openings, and other special details so that the detail and fab requirements can be understood. Make sure to note that main member reinforcement is not considered connection material. So this needs to be designed by the engineer of record regardless of the option selected at, and this is for any locations away from connections. Member reinforcement is needed at locations of connections where members are framing in. The engineer then has 2 options available. We'll summarize the 2 options. 3A, the engineer of record can they can design the member reinforcement at the connections. For option 3B, the EOR provides concepts and estimated quantities so that the quantity, detailing, and fabrication requirements can be readily understood. And if there are no quantities or conceptual configurations are shown, member reinforcement connections will not be included in the bid. Subsequently, member reinforcement at connections, where required, shall be designed in its final configuration by the licensed engineer in charge of connection design. This is basically so that that going into bidding, there's an equal playing field for everybody bidding the project. Everybody's bidding the same thing. I want to make sure to note that AISC has a free useful tool, Clean Columns program, that can help determine required column sizes to omit member reinforcement and possibly save costs. There's also there's an article written in October 2017, Modern Steel Construction, by Larry Muir, called "Reinforcing the Point." This does a really good job. This article does a really good job of explaining in detail options 3A and 3B, and also provides quite a few examples. So when the engineer of record chooses option number 3 per the Code of Standard Practice, what must they provide? There's a lot of different connection types available for the fabricator to choose from. So the engineer of record needs to provide guidance if there's any specific type that they're looking for, whether it's architectural or structural requirement. This is so the fabricator is not repeatedly revising and resubmitting shop drawings, which can be time-consuming and expensive. Option number 3 also requires that all loads are shown so that the connections can be adequately designed. So continuing on with the engineer of record requirements for option number 3, they also need to describe whether the loads provided are in the service level or factored. They also need to describe whether the connections are to be designed in LRFD or ASD. They also need to list any substantiating information required. Basically, what information do they want to see submitted with the shop and erection drawing submittals? And are the substantiating information going to require a PE seal, and what specifically do they want sealed? I wanted to make sure to note that the Code of Standard Practice in the commentary states that it is not recommended for the engineer of record to require a PE seal on each shop and erection drawing. Section 4 of the Code of Standard Practice describes the requirements for submittals by the fabricator when option number 3 is selected. First, the fabricator needs to submit representative samples of the connections, both sketches and calculations for the different connection types. This just helps to make sure that everybody's on the same page before performing a thorough design of the connections. The engineer of record then needs to confirm in writing whether the samples are acceptable, or if not, what modifications are required so that they will be acceptable. Continuing with the requirements for the fabricator for option 3. The fabricator's connection designer reviews shop drawings and erection drawings, and they must make sure that they correctly incorporate their connection designs. The fabricator also has to provide a clear way of referencing between the connection design and the shop erection drawings. Also spelled out in section 4.2.3, if the fabricator wants to make a change to a connection detail that's been specified by the engineer of record in the contract documents, the fabricator needs to submit these change requests in advance. It can't just show up as a surprise on the shop and erection drawings. The EOR then needs to review and approve or reject these requests. So to summarize the Code of Standard Practice, Section 4 on approval documents. The owner, through the engineer of record, delivers the design documents. The fabricator then makes approval documents, which they now have two options available. They can use either physical shop drawings, which has been historically done, but they can also now use a model for the approval documents. These approval documents are then reviewed by the ODRD, which is the engineer of record, or the and then the ODRC, basically the general contractor or construction manager, before release for fabrication. Even after these reviews, the fabricator is still responsible for dimensional accuracy and fit up. Here's a visual representation of the approval document flow when using option number 3. So you can see the engineer of record provides design criteria like the loads and any different restrictions on the connection types. The licensed engineer in responsible charge of the connection design, the connection designer, prepares substantiating connection information, including calculations. The detailer then incorporates connection design on the shop drawings. The connection designer must then review the approval documents to ensure that the connections are incorporated properly. However, the engineer of record must still review and approve the design, as they have the overall best knowledge of the building as a whole. Now we're going to take a look at the Code of Standard Practice in Section 4 and see what it says about requests for information, which are commonly referred to as RFIs. So RFIs are a written record of questions and responses between the fabricator and the EOR. Important to note that it's not intended for the incremental release of construction of design drawings. So here's some key points that are listed in the commentary of Section 4 on RFIs. So the process can be used to develop corrective measures to resolve errors. Should not be used to replace all verbal communication. That's not its intended use. RFIs require a standardized format that includes a unique RFI number, the date, author, and one important thing that needs to be included is the needed response date. Need to limit one question per RFI, and once a RFI is responded to, this constitutes a release for construction. All right, so now we're through the Code of Standard Practice, through the items that apply to connection design. So now we're going to take a look at the process a connection design engineer goes through during the bid phase of a project. So we would get a call from the fabricator saying they're looking at a project where the engineer of record has chosen option number 3 from the Code of Standard Practice, the delegated design option. So then the fabricator would send us the design drawing and ask for us to develop the scope of services and then also a corresponding fee for those services. So the first thing we need to do is to determine exactly which connections will need to be provided. So many fabricators use some type of detailing software now that can also perform connection design and are capable of providing a variety of different types. So we would just need to know which ones the software could handle for this specific project. Along with this, many times, even though the detailing software can output calculations, the EORs will require the connection designer review and seal these calcs. So it's not a lot of fun to review pages and pages of computer output, but sometimes it is needed and required. Also, some fabricators have already created their own internal standards for their preferred connection types, and these already have their own supporting calculations. So they wouldn't need help with those. So in the bid phase, when looking through the design drawings, I'll look for all those items that were spelled out in the Code of Standard Practice, which we've already touched on. So I'll look for whether there's nominal or factored loads, whether the connections need to be in ASD or LRFD. Keep an eye out for any specific welding or bolting requirements. We'll also look at the description for the lateral load resisting system, which is a requirement in Section 7 of the Code of Standard Practice, which I'm sure will be highlighted in the erection portions of Night School 18. And so I'll just use this to help try to understand how the lateral loads are resisted and how they travel through the structure. Per the Code of Standard Practice, the engineer of record may specifically design some connections themselves and delegate others. So we'll look through the detail sheets and see if there are already some that are completely designed by the engineer of record. And when we do that, we also keep a lookout for details that appear that they might be copied from a previous project. So this can kind of throw off a red flag that these details might not be telling the whole story. Also, when we're reviewing the design drawings, we'll look if there's any architectural or structural requirements that require specific connection types. As an example, we'll look at the moment connections and see if there's a fully restrained requirement or partially restrained. So when bidding a project, we'll start reviewing the drawings and basically start counting up the number of different connections that are going to need to be designed. So when reviewing simple shear, the engineer has 3 ways that they'll typically provide loads. 1/2 uniform dead load, which is not recommended and will lead to overly conservative designs. They could also specify charts where each section set, as shown on the right, has a shown load. Or they can provide specific loads for each location, which is actually the preferred method and will lead to the most efficient designs. We'll also start looking for shear loads that will put designs outside of the standards provided in the AISC manual. A lot of times this could be stocky sections that may have been designed like that to reduce story height, or beams that possibly have long unbraced length. These stocky sections end up with limited room for connection materials in the web. Also keep an eye out for beams with long copes, skewed beams, sloping beams. All of these will typically require their own specific designs. We'll also look for multiple members that are framing it at a node, because we know this is going to make the design more complicated. Also elevation differences at beam to girder connections. And then finally, axial loads and beams. When there's axial loads and beams combined with shear, it's typically going to require more analysis and more time to design the connection. When reviewing bracing connections, again, we're looking for a count of the different number of designs. So we're keeping an eye out for loads, brace sizes, geometry. We'll also look at the beam sizes at the brace nodes, which will make a difference in the load distribution due to the uniform force method, which we'll touch on a bit more later. We'll also look at whether these brace nodes are into the column web or the flange, because this will also change the loading distribution. We'll also look and review the options for the end of the brace connections, whether they can be field welded or bolted. We'll also keep an eye out for additional members framing into these brace connections as they can complicate the nodes, whether it's perpendicular beams framing in or possibly horizontal bracing. And then when reviewing moment connections, it's very similar. Again, we're looking for different sizes of beams. We're looking for different loads, whether there are bolting or welding options or requirements. We'll also take a look to see if the engineer of record fulfilled the Code of Standard Practice requirement for option number 3 and provided information on the column reinforcement requirements. And again, keep an eye out for additional members framing into the node. This could potentially increase the complexity. Then at the end of the review, we'll summarize all of the different connection type totals and approximate a time required for each different type, and then just summarize an estimated fee. So I listed here some of the items that will impact costs for connection designer. First of all, a lack of information. Costs are going to go up because I know I'm going to have to write a bunch of RFIs. For a lack of clarity, again, going to have to write many RFIs, slows down the process, multiple iterations. We see obvious errors. You know it's going to be redesigned. It's going to slow down the process and cost more. Then one good note is that more repetition in sizes and forces really helps to decrease design costs, which also will decrease detailing costs and likely fabrication costs. Finally, main member reinforcement. It's not only costly to the fabricators, but it also creates more work in designing and detailing the connections, likely requiring special designs for members that are framing into the column web where these stiffeners or doublers are present. So here's an example of a frame where member repetition and consistent spacing in the bays and in the elevations allows for more efficient connection design and in turn detailing and fabrication. You can see from the picture the beam sizes, repetitive, brace sizes, repetitive. The elevations and the bay spaces are repetitive. And the picture on the right, that chart, shows the cost breakdown of approximate cost breakdown of a structural steel building. And so the material can vary from 20% to 35%. But the important point is that less weight is not necessarily less cost. So upsizing members for repetition is generally a good thing. Now we'll take a look at the steps a connection design engineer takes at the beginning of a project. So we get a call from the fabricator, great news, we got the job. So okay, what do we need to do to get started with this project? So the first thing we're going to do as a connection designer is to start to compile a list of RFIs, requests for information. So we're going to look at the loading. We're going to look for excessively high loads, nodes where the envelope forces are unclear or don't reach equilibrium, or possibly even missing loads. Also, as I stated before, we'll make sure we know and understand the lateral force resisting system that is required for the Code of Standard Practice in 7.10. The RFI process we will also use to request alternates that will help with shop and field efficiencies. So we'll send sketches for the alternates, and for an example, you can see on this sheet using a field bolted substitution is common. The example here shown is using an HSS brace bolted connection rather than a field weld. We'll also request to upsize some main members. If column stiffeners are required, what size column is needed so we can omit these stiffeners. And similarly with long cope beams or high shears that will require beam web reinforcement, we'll also upsize the members. For instance, request to upsize a W8 to a W12 so that the beam web does not need to be reinforced. Continuing with the initial request for information list, we'll also look at bracing work point verification. The picture on the left, you typically want to see the work lines come to a common work point. And the example on the right, which we'll look at a little bit more in depth later, would generate an RFI to get verification on the work lines. And then for complicated nodes or where there's a substitution is being requested, we'll send sample concepts, make sure everybody's on the same page. The engineer of record understands what we're trying to do and what we'd like to substitute. No surprises, and hopefully avoid any significant redesign. So the next step after the RFI process would be to review with the client, the fabricator, their preference for each different type of connection. So we'll talk with the fabricator about their cascading preference for simple shear. For example, their first choice would typically be a shear tab or a single angle, and if not enough capacity, then move on to a double angle. We'll also talk about their preferred bolt hole types, whether standard or short slots. The picture on the right, you can see in the outstanding leg the typical use of short slots in either a single angle or double angle connection. And then if there's moment connections in the project, we'll talk about the different connection type preferences, whether the fabricator would prefer to use flange plates, end plates, whether field welds are required, or if bolting is possibly an option. And then if we're using bolted connections, we'll want to talk about whether they prefer to use bearing or slip critical, with a trade-off between the amount of bolts versus erectability, basically. Less bolts are typically required for the bearing connections, but it's generally easier to erect with slip critical bolts, which would allow the use of oversized holes. Similarly for bracing, we'll look at what type of connection options are going to work well for this specific project and whether we prefer or are able to use slip critical bolts instead of bearing. Also important when beginning a project, we'll work with the fabricator to select a couple different bolt size and grade types. Typically, we'll use one size for lower load requirement connections, for example, shear connections, and then maybe a second bolt type for higher load connections, for example, bracing or truss connections. It's important to note that the bolt diameter selection needs to be at least a 1/4 inch difference between the bolts to avoid accidental installation of bolts that are too small. For example, if we selected 3/4 inch and 7/8 inch diameter bolts on a job, it opens up the potential to put a 3/4 inch diameter bolt in a hole that's intended for a 7/8 inch diameter bolt. We'll also talk with the client about their bolt installation technique and the equipment that's going to be used for these bolts. And finally, we'll talk about repetitive material preferences. If there's a certain angle size that they like to work with that they standardly keep in stock, or if there's a minimum plate thickness that they prefer to work with, we'll try to accommodate that for them. We'll also go into the preferred weld types. Fabricators will generally prefer fillet welds, single pass if possible, which is 5/16 inch or smaller. And fillet welds are typically fairly efficient up to about 3/4 of an inch. And then if partial joint penetration welds are to be used, what's their preferred type? We'll also need to know the process for certain PJP welds, as that will impact the effective size, and we'll talk about that a little bit more later. And then finally, complete joint penetration welds, similar to PJP welds. What types are preferred? Which can depend on what pre-qualified procedures and qualified personnel the fabricator has available. Now I'll talk about some of the common challenges we run into when working on a connection design project. So the things that a connection designer needs to know to design the connections were spelled out in the Code of Standard Practice. And so it's basically the same as any statics problem. We treat each connection as its own free body diagram, which means we need to have a clear understanding of both the load and the load path. This slide shows all of the different minimum limit states that need to be checked when designing connections. As we pointed out in the previous slide, we need loads so that all of these different items can be checked. So J2 of the specifications talks about welding requirements. J3 has the bolting requirements. J4 has all material checks for connecting elements. And then if using HSS or pipe sections, then need to reference Chapter K. The communication of loading, particularly envelope loading, is a common issue that comes up. So the EOR designing a building, they may have 50 different load combinations, which result in maximum and minimum loads for different members. And many times these loads are not in the same loading combinations. And so when these loads make their way onto the design drawings, it can be confusing. Many times you'll end up with through forces, and you're not sure if they really are through forces intended there. And many times the nodes will lack equilibrium. So here's just a sample RFI that we would send when trying to gain clarification on the envelope loading to really see if there really are through forces at this node. If you remember, I showed this this design drawing detail on a previous slide, highlighting situations where RFIs would be needed for clarification. In this case, eccentric work lines and loading verification. So the design drawing on the left, and then the actual design connection is on the right. Make sure to note the moment that's developed by the work lines being offset by 8 inches. There's no moment listed in the design drawings, so something like this really puts up a red flag that there's a potential serious error. With the possibility that's a modeling issue, is the engineer aware of the moment? They possibly might have their work lines lined up in their analysis model. And if there really is a moment, where does it go? And just verify that there aren't any members that need to be upsized. Long copes can cause problems when shallower beams frame into girders with wide flanges, also possibly with thick flanges. This can limit the amount of room for connection material and may also cause limiting failure modes in the web itself, whether it's flexural buckling or block shear. Long copes may require reinforcement of some type, and in Part 9 of the manual provides help with providing a procedure for checking these cope sections. Here's an example of a long cope that's created by a small W8 beam framing into a larger W36 girder. The cope is also increased due to the W8 framing in at an angle. So from the plan view, with the line drawing, it doesn't look too bad. But when we look at the members and their actual isometric size, the problem's pretty apparent. So in a case like this, a flexural buckling issue is likely with a cope length of 12 inches and then a very thin beam web of only 3/16 of an inch. So this would be a good example of where we would ask for upsizing to possibly a W12 shape sent through an RFI. Here's one way of dealing with a long cope by using the connection material, in this case a bent plate, as reinforcement of the beam web by extending the plate beyond the cope section location. So the AISC manual provides some helpful options in Part 9 for reinforcing beam webs at cope outs, whether it's adding web doubler plates or stiffeners, either longitudinal or transverse. So you can see the figures here from Part 9 showing these different options. Similar to single copes, double copes can create connection material limitations and possibly the need for web reinforcement. Double copes occur when a member frames into a section of the same size or shallower, for example, a W16 to a W16. So you can see that the double cope in the figure on the right, you just end up with a plate section remaining to resist the bending moments. And again, very susceptible to flexural buckling issues. And again, we would look at upsizing the girder so the bottom flange does not need to be coped, sent through an RFI process. So for example, we would ask to change the shape so that the W16 frames into a W18. As we talked about a little bit previously, high shear connections can result from the engineer of record specifying the 1/2 uniform dead load, which creates really high shears for short span beams. Also, the stocky sections can limit the amount of room in the web for a shear connection. This can possibly result in the need for web reinforcement or connections with multiple columns of bolts, or we may even need to extend the web below the bottom flange as shown in the example on the right. So these types of connections are an instance where I would request actual loads from the engineer of record in the form of an RFI in the hope of avoiding a costly design. Top of steel differences can result in beams needing bottom flange coping. You can see here in AISC figure 10-32 helps provide guidance as to some options when this type of framing situation occurs, using either a double angle or a plate to create a landing surface. Oh, I think sorry, let's go back. I skipped a slide. All right. So skewed beams, or those that frame in on angles as shown on this picture, can create the requirement for some unique designs. Typically, single-sided shear tabs can be used for angles up to 45 degrees. And AISC table 10-14C is a very helpful guide to determining required weld sizes for these tabs. Bent plates are usually the most efficient solution for angles over 45 degrees. But there can be a limitation on the thicknesses of the plate that a fabricator can bend. And then skewed beams, as we've previously shown, can result in long copes with the potential need for web reinforcement. Skewed beams can also create bolting access issues. And then when skews frame into columns, it can also create some ugly connections, possibly with weld access issues. So this is another situation where I might send an RFI, and in this case would be to slightly adjust a skewed work line to help clean up the connection. This will make a little bit more sense now. So the top of steel differences can result in beams needing bottom flange coping. So this figure from AISC 10-32 helps provide some guidance for the options, either using a double angle or a plate for a landing surface. One thing to note is that the angle or the plate can be extended back into the web of the beam if you run into problems with the cope section bending. One thing to watch out for when designing seated connections, when on a bearing plate or framing in above a girder, is top flange stability, which is discussed in section J 10.7 of the specification and also part 2 of the manual. So beam capacity is dependent upon having torsional restraint at the ends of the beam. So this could be decking, a brace to the top flange. And if there's no decking present, another common option is to provide stiffeners or end plates at the beam, shown here on figure 2-1. Here's a good example of challenges that can be created by having too many members framing into a single node. So the line drawing on the left, which looks fairly harmless, and then the two-dimensional connection detail on the right that shows the actual shape widths and also the connection material lengths. Again, this is an instance where with many members framing into a common node where we would need to ask for more information on loading through an RFI. So here's what that same node looks like when modeled in a detailing software. So it's recommended that the engineer of record look for ways to avoid multiple members framing into a single node. Building information modeling can be a really helpful tool. The 3D view modeling can really help identify these potential issues up front. And then AISC Constructability Design Guide number 23 discusses this in greater detail and provides some good options to simplify framing. This is another example of how line drawings can sometimes be deceiving. The structural analysis model on the left, and then the actual Tekla 3D detailing model on the right. So this is another important note that this example really illustrates, is that for some structures, connection material can add up to a significant amount of the total tonnage, varying from 5% all the way up to 30% of the total tonnage. We also have to keep in mind the erector when we're designing connections. We need to make sure we keep our iron workers safe. So some erectability safety issues are addressed by OSHA, which is conveniently located in Part 2 of the AISC manual. These discuss the minimum bolt up required when erecting steel members. Another common situation that comes up is when there are opposing beams framing into column webs or girders over columns. This requires that the fabricator provide either a staggered connection, as shown on the right, or an erection seat, as shown on the left. So what these connection types allow is so that the beam that was first erected can remain supported while the second is brought into the joint and bolted up. Column base plates, when freestanding during erection, also have their own specific OSHA requirements. They must have 4 anchor rods, and they also must be capable of safely resisting a 300-pound force located 18-inch from the outer face of the column in any direction. And so this really needs to be included as a load combination for whoever is designing the base plates, which would typically be the engineer of record. Column stiffeners can create limitations on the type of connections that can be used for the beams framing into the column web, both due to erectability and access issues. So a commonly used connection type for situations like this would be an extended shear tab, which is discussed extensively in Part 10 of the manual. The manual also has a discussion on the possible eccentric impacts of using this type of connection. Moment connections through girders can sometimes get pretty ugly and expensive depending on the members that are selected by the engineer of record. So the example on the left shows different depth opposing beams, resulting in the need to develop a false flange to transfer the flange forces. And then the connection on the right shows what can be required and how complicated and expensive the welding can become when the girder depth and the flange thicknesses are not compatible. Another common problem is trying to develop moment connections for beams with 4-inch wide flanges, which doesn't leave enough room for a bolting option. So these are all examples of situations where we would likely send an RFI to the engineer of record asking for a specific shape substitution. The shape would likely be heavier, but still more efficient for the fabricator. Axial loads in beams and girders can require unique designs depending on their magnitude. Typically a double angle end plate or shear tab can be used for smaller axial loads where the web is suitable to handle the combined axial plus shear. I do need to pay attention though to the bolt types used here, as some hole types such as short slots or long slots cannot be used in these situations where bearing bolts are being utilized. And then for larger axial loads, the flanges will likely need to be engaged, which would lend itself more to the use of flange plates or end plates with the flanges connected. This is probably a situation where I would ask the engineer of record if they have a preference when engaging the flanges for an axial load, as engaging the flanges might create additional stiffness that they had not accounted for in their analysis model. Next, we'll get into some basic recommendations and resources available to help facilitate efficient connection designs with consideration of both the shop fabrication and field erection. So with material selection, it's the same as building design. We want to select materials that are readily available. So tables 2-4 and 2-5 of the manual are helpful in determining what to select. With wide flanges or WT shapes, we use ASTM A992. A36 is still the default for I shapes, channels, and angles. And then for plates, there's not really much of a cost difference between ASTM A36 and ASTM A572. 572 is grade 50, so sometimes this can be advantageous in decreasing costs. And once again, the cost of a steel building is more about time than material. So really we are looking to try to minimize the amount of time the fabricator spends handling material. So to do this, it's recommended to use a couple groups of angles, plates, WTs. This may result in connections being over-designed, but it's still more cost-efficient overall. One thing to remember is that a WT shape is just a W shape cut in half. So if specifying a WT, then take a look for a W shape that's already used on the job. With stiffeners and plates, try to maintain the same width as much as possible. Full depth and full width stiffeners are not always required. And it's good to know that plate is delivered in bars, which was covered in AISC covered in presentation 18.3. They're just strips of plate, so you can reference a local steel supply stock list to see what they keep stocked, but try to stick with these widths rather than an odd 1/16 of an inch, which will require additional cutting. So when designing connections, we'll try to move as much of the work as possible for fit up and assembly to the shop, as labor is more efficient here, tools are more readily available, access heights are lower, weather is controlled. This typically, though not always, means shop welding or bolting and then field bolting. And we also need to stay aware of shipping restrictions. We don't want to create connection nodes where an oversized load is required. That can get expensive with permitting and escorts. We also want to keep an eye out for material that could possibly be shop attached, such as short cantilever beams. When determining bolt selection, it's good to know the general advantages and disadvantages of bearing versus slip critical bolts. So bearing bolts provide the advantage of higher capacity, they're easier and cheaper to install, and depending on the installation technique, could mean less access room required for installation. Some of the disadvantages are their limitation on bolt hole type, which in turn can make fit up more difficult. Bearing bolts may also not be suitable for certain joints that will experience load reversals and cyclical fatigue. Now for slip critical bolts, which rely on friction for load transfer. Some advantages are that they can be used with all different hole types, which in effect can make erection easier if using oversized or slotted holes. They're also suitable for load reversal or fatigue applications. Some of the disadvantages are that they cost more to install. The friction developed requires material surface preparation and then protection. Slip critical bolts have lower capacity, so thus more are needed. And also, once pre-tensioned, grade A490 bolts may not be reused. Now for our other method of joining materials and connections, welding. So fillet welds, as I previously noted, are preferred by fabricators. They're cost efficient up to about 3/4 of an inch and typically don't require any base material cutting preparation. Again, try to keep the single pass if possible, which is 5/16 of an inch or smaller. And then table 8-12 in the manual is really helpful in showing the number of passes required for each weld size. So then you can get an idea of the relative costs. It shows the weld passes for fillet welds and then also for groove welds. Something to keep in mind when designing fillet welds is equation J2-5 in Chapter J of the specification. This equation allows for up to a 50% increase in fillet weld capacity depending on the resultant load angle. And then figure 3-16 helps to show what is meant by parallel loading versus transverse loading. Partial joint penetration welds typically come next on the efficiency spectrum for fabricators and are preferred over CJP welds. Base material preparation is typically required, and AISC design table 8.2 shows the PJP pre-qualified welds. It's good to make sure to note that effective weld thickness of groove welds depends on both the weld process and the preparation angle. AISC table J2.1 shows how to determine this effective weld size. It's also good to note that groove welds with an 1/8" LAN are generally more cost efficient than a CJP weld of the same size, even though more base material is required. This has the impact of removing the requirement for a backer bar. So you can see circled in the upper right shows what I mean with an 1/8 of an inch material land. When specifying partial joint penetration flare groove welds, which are common at HSS sections, that the effective weld is a function of both the welding process and also the material radius. The material radius is a function of the material thickness, so there's some digging around to do there to determine effective weld size. And you can reference table J2.2, shows these effective weld sizes. CJP welds, which are the most expensive for a fabricator due to the required material preparation, backer bar installation, the more stringent weld inspection, and they also require highly trained and certified welders. You can reference table 8.2 for the CJP pre-qualified welds. And one reason we probably see them more often than we should is that CJP welds develop the full strength of the base material, so the calculation is really easy for the designer. When dealing with clearances, there's no point in designing something that can't be built. So some important references to watch. With weld access, you want to look at figure 8-11 to see the minimum degree that can be used when determining if there's enough access room to properly apply a weld. Also, fillet welds require minimum shelf lengths due to material tolerances. Figures 8-13 and 8-14 are helpful to figure out what amount of excess shelf material is needed. This can be critical when designing connections for cope beams where material length is restricted, as you can see there in figure 8-14. Similar to welds, we also need to be aware of the space limitations needed for bolt installation. J3.2 of the code specifies minimum bolt spacing, which is 2 2/3 times bolt diameter, although 3 times the bolt diameter is recommended. AISC tables 7-14 to 7-16 are very helpful in determining what clearances are needed for bolt installations. They even break down the required clearance as to whether pretension bolts are being utilized. Another helpful reference if you're trying to squeeze some connection material into a tight location within a rolled shape is figure 10-3. This figure shows the allowable encroachment allowed, commonly called riding the fillet. And then when determining minimum required edge distances from bolt holes, make sure to reference table J3.4. Another common way to place more bolts into a dimensionally restricted area is to stagger the bolts between rows and columns. AISC table 7-15 shows the required clearances due to tightening tool access when utilizing staggered bolts. So many of these charts that we've been looking at reference the K dimension, which is a radius which is the result of the rolling process for these shapes, which we've learned about in the second presentation in this series. So when checking clearances, make sure to use the K detail dimension shown in the manual in table 1-1, whereas when performing calculations, it's appropriate to use the K design value. You can see those circled in red on the figure. Also, whenever bolting into the flange of a wide flange or WT shape, try to use the standard gauge spacing listed in that same table, shown here in the blue circle. Similarly, when bolt holes are designed in angles, make sure to reference table 1-7A for the standard workable gauges to locate the bolt holes whenever possible. When getting into designing bracing connections, there are some helpful references for bolting options for the ends of braces. So with wide flange shapes, Design Guide 29, Vertical Bracing Connections Analysis and Design provides good guidance. And then when dealing with HSS brace shapes, Design Guide 24, Hollow Structural Section Connections can also be a valuable resource. Another item to be aware of that, that relates to erectability is when designing brace connection gussets. So a couple years into my career, I was working on some gusset design for HSS braces that were to be field welded. So I designed all the connections with the braces squeezed in as closely as I could to the beams, thus limiting the connection material as much as possible. So I spent about a week designing these when my project manager looked them over and asked the simple question if I had checked to see if they could be erected. And then sure enough, when looking at the brace bay overall, there was no way that the braces could actually be brought in and rotated into position. So I had to spend a whole week redesigning the connections. So it's definitely something that I remember. So it's important to take a step back and think about how things are going to be built. In this case, we had to revise the connection to show a maximum setback to the end of the brace, which would then thus allow the detailer to place the brace end where needed to make sure that they would fit in the field. A couple helpful references when designing gusset plates. If you end up with bending in the gusset plate, make sure to use AISC specification F11 for analysis, and then section H1 for combined axial plus bending. Design guide number 29 includes a helpful chart shown below to guide in determining effective length factors for gussets and compression. And then AISC table 4-14 provides critical compression stress based upon KL over R values. So another incredibly valuable resource for designing brace connections is the uniform force method, which is included in part 13 of the manual and also covered extensively, including examples in design guide number 29. So it's a great resource. It breaks up the force components to each gusset contact surface. It's very logical. It's easy to follow using basic statics, and it also results in very efficient designs. The uniform force method also includes three special cases. One, you can shift the work point for simplicity. Two, shift delta VB, which we'll talk about in a second. And then the third one addresses gussets with only one connection face. So I personally found special case number 2 to be especially valuable. This case allows you to shift the brace vertical load component, V sub B, that is transferred to the beam and instead direct it through the gusset to column connection. So this can help when you end up with having issues with overloading of the shear strength in the beam web to column connection. We've already discussed skewed beams a little bit previously, but I'll summarize again. For skews up to 45 degrees, a shear tab is preferable, with welds as shown in table 10-14C for plates up to 5/8 of an inch. And then after 45 degrees, the use of a bent plate is recommended, with figure 10-36 of the manual showing options. A couple notes of caution when using the uniform force method. When framing into a column flange, the force breakdown will result in transfer of horizontal load through the connection between the gusset to column and also beam to column. So this connection type typically is a double angle, and this will result in prying of the bolts in this connection, something that needs to be taken into consideration. Part 9 of the manual addresses how to calculate these additional prying forces, with figure 9-4 providing an explanation of the variables. It is also possible that bending will be transferred to the gusset to column connection. AISC manual part 7, shown here in figure 7-6, provides a logical way of how to address this by using 1/6 of the length of the double angle, or the WT, to locate the neutral axis and thus calculate the tension forces in the bolts. So the skewed beams again, for skews up to 45 degrees, shear tab is preferable, with the welds as shown in table 10-14C for plates up to 5/8 of an inch, and then after 45 degrees, the use of a bent plate is recommended. And then for checking the clearances of skewed beams, reference tables 10-14A and 10-14B. Also need to mention that bent plates require consideration of eccentricity in design. This is discussed in Part 10. And then when specifying a bent plate, Table 10-13 is helpful for determining the minimum cold bending radius for different thicknesses. But again, I would still check with the Fabricator to see the maximum plate thickness that they are both comfortable and capable in bending. Now where moment connections are required, a common connection type is bolted flange plates, where the plates are shop welded to the column and then field bolted to the beam flanges. Fabricators will typically oversize the depth dimension between the flange plates to account for beam depth variations due to the mill rolling process. You can see this example with the gap noted circled in red. Then when the beam is erected, either fills or shims, which are just thin plates, will be used to fill the remaining gap. We do need to be aware, however, that this can cause a required reduction in our bolt capacities. So when using bearing bolts, reference specification section J5.2, whereas it currently stands, gaps over 1/4 of an inch require a reduction. And then if using slip critical bolts, you'll want to reference specification section J3.8, which requires a reduction when more than one fill layer is used. Another helpful tip is to design the flange plates either wider or narrower than the beam flange widths. This will allow room for fillet welds just in case the bolt holes between the plate and the beam flange don't align in the field. Another bolt-up moment connection option are extended end plates, which are described in depth in design guide number 4. So this is another connection type that may require shims between the end plate and the column flange. So it's another thing to keep an eye out for possibly reduced bolt capacities. So now we'll just run through some good connection design references. For bolting, part 7 of the AISC manual, and then also J3 of the specification. RCSC specification for structural joints using high-strength bolts, which is located in section 16.2 of the AISC manual. And then AISC Design Guide 17, high-strength bolts, a primer for structural engineers. Getting into welds, part 8 of the manual, J2 of the specification, AWSD 1.1, which is the structural welding code for steel, Design Guide 21, and then outside of AISC, Omer Blodgett's Design of Welded Structures is very valuable. And then also a good reference in there is the properties of a weld treated as a line when need to performing elastic analysis. For simple shear connections, Chapter J, and then parts 9 and 10 of the manual. For HSS connections, Chapter J and Chapter K. And also AISC Design Guide number 24. Looking at moment connections, part 9, 11, and 12. Also Chapter J again, and then there's three valuable design guides there, 4, 13, and 16 that can be helpful. All right, I think it's time to hand it off to Brent for any additional questions. Yep.
All right, thanks, Chad. We do have several questions to get to from our audience, but as we do every week, we have a couple polling questions for our audience to check in to see if they've been following what's been presented this evening. All right, so here's our first polling question. According to the Code of Standard Practice, main member reinforcement at a connection location can be delegated to the fabricator's connection designer. Is that true or false? According to the Code of Standard Practice, main member reinforcement at a connection location can be delegated to the fabricator's connection designer. True or false? Just simply click on the radio button for the answer you think is correct and push submit, and it can be part of the data that we receive. All right, I'm going to go ahead and close the poll, Chad. We have a 58% said false, 42% said true. What do you think, Chad?
Yeah, so the looks like we're a little bit off on that one. So the answer is true. For option 3, the main member reinforcement can be delegated to the connection designer. I don't know if we want to bounce back to that slide, Brent.
Sure. Get there quickly.
Like 17.
17.
So option 3B here, the EOR can provide project-specific conceptual details and an estimated quantity for bidding purposes, but they actually delegate the design of the connections at the member reinforcing to the connection designer.
Okay, let's do one more here. See how we do on this next one. Which of the following allows for more efficient design of connections? Is it A, repetitive sizes in framing members? Is it B, 1/2 uniform dead load used for determining shear loads? Is it C, repetitive geometry? D, both A and C, or E, all of the above? Again, we're looking for which of the following allows for more efficient design of connections. Give people just a few more seconds here. All right, in a landslide, everyone said D, which is both repetitive sizes in framing members and repetitive geometry. Do you agree, Chad?
Yeah, that one looks good.
Right, very good. All right, let's get to some questions here with the time we have left. The first question is the AISC Code of Standard Practice legally binding in law?
I'm pretty sure that once you specify the AISC specification, then that becomes the legally binding language.
Okay. All right. Have you ever run into where a local or state agency requires one of the 3 options for connection design?
A state or local? I've never run into that. I've never run into that situation before. I can't say that I've seen that before.
Okay. We'll move on to our next question for you. This person says they have seen lately, they've seen a lot of drawings where the EOR is specifying slip critical connections. Have you seen this before, and what can be done at the connection designer's side when the steel notes say that all connections should be slip critical?
I don't know if there's a specific situation why they feel like they would want slip critical. There might be some load reversal or some special loading that they're looking at. But again, this would probably be one where I would send an RFI or just give them a call and see exactly what they're thinking and why they feel like slip critical bolts are needed.
And this is the operator. Looks like we lost connection with Britt.
Okay, thank you. Keith, are we live right now?
We are live still.
Okay. All right, everyone. Seems we have some technical difficulties with Brent's microphone, and we're actually at full time here for this week. And so if we happen to not have gotten to one of the questions that you posed,
Brent's with us right now.
Okay, Brent, you wanna take the floor back?
Thanks, Nate. Sorry about that, everyone. My phone dropped on us. Apologize on that. Okay, let's go to slide 19, Chad.
Okay.
The question is this: if the EOR insists on his requirement to sign and seal the shop drawings and erection plan, what else can be done on the part of the connection design engineer?
Yeah, I think we've run into this before, and we've had to do that. We've had to sign and seal every drawing. So, I don't know if you could get in touch with some people at AISC. They might be able to help back you up or point to this portion of the commentary within the Code of Standard Practice. But I have seen it before myself where everything is actually required to be signed and sealed.
Okay, and then moving on to slide 37. The question regarding transfer forces. When the EOR provides transfer forces through an RFI response, meaning they were not provided during the bid stage, can that be considered a change in the contract documents?
I mean, I'm not a lawyer, but I would think that yes, if they're changing the contract documents, and a through force can result in some significant change in connection designs and the material required. I think that's a legitimate change.
I guess along those similar lines, if you have an RFI that you send, for example, for a cope on a skewed beam connection that requires either a member size increase or additional plates, are those typically change orders, or is that part of your risk as the fabricator's representative?
Yeah, as the fabricator's representative, we wouldn't be asking a question like that unless we thought we could make the design more efficient for the fabricator. So from a fabricator's perspective, I mean, the change wouldn't be an increase in cost for them. Hopefully that's the point they were getting at.
We'll get to just a couple more here and then we'll wrap up. On slide 23, you indicated that it may be acceptable to submit a model instead of traditional shop drawings. Is the EOR required to accept this, or can they insist on traditional drawings?
That's a good question, and that's one I would I'd have to refer to AISC. I'm not sure if they could demand the model. They might be limited in their own software, so it could be a legitimate concern for them.
Okay, and get to one more question, and then we'll wrap up here. Take us to slide 69. Just on 69 and 70, these two slides on bolting, you state that bearing bolts are stated as easy to install and slip critical stated as easier to erect. Can you please expand on this or explain the difference in that description?
Yeah, I guess I should have been a little bit clearer. I guess with bearing bolts, there's less installation tools needed. As long as the holes line up, it's quicker and easier. But with the slip critical bolts, when you're using oversized holes or slotted holes, there's room for error, so you're less likely to run into any type of erectability issues in the field.